Hello everyone. This is a small 5 minutes talk about the presentation that we will do at the Keystones conference. So this work is an extract of a longer work on bias and variance in cryo-electron microscopy. So bias and variance are two statistical concepts that are very well defined. So just intuitively, so let's say that we have to estimate a parameter, and in CryoEM, our main parameter is the volume that we are interested in. So you make an estimate of what that parameter is, and you get a point. So the true volume or the true parameter is at the center of some landscape. So this is the set of all possible volumes. This is our estimated volume. This is the true volume. So the distance, the difference between our estimate and the true volume is called the bias. If we repeat this process of estimating our volume multiple times, with subsets of the images, or because we have another collection from the same sample, then we would have multiple volumes. And the dispersion of all those volumes is called the variance. So we would like to be in a situation in which we have low variance and low bias. Well, so the bias is the difference between the true volume and our estimated volume. And beside this difference that we will think of it as a deterministic thing, we have the random noise. So actually, when you have when you have a set of images and you have to construct the volume, what you have is to estimate the parameters of those images, so the orientational parameters of those images, so that they can be combined into volumes. So having bias in the volume is caused by having bias in the estimation of the alignment parameters. So let's say that we have n1 numbers that have been correctly assigned to a class, so we may have also multiple classes, and they have been correctly aligned, and n2 images that have been incorrectly assigned or aligned. So our estimate of what is V1 will be this addition here. So this is a weighted sum between the N1 and N2 images. And you may reorder this so that you have that your estimate of V1 is the true V1 plus something. So this plus something depends on two things. What is the fraction of images that have been incorrectly assigned or aligned, and also what is the difference between V2 and V1, because you may make a lot of mistakes of incorrectly assigning to V2, but then if V2 and V1 are so similar that you wouldn't see this difference into the reconstruction, in which we have too many parameters to estimate with respect to the number of observations. We are in the opposite regime, so we are here. So I think that we are used to in CryoEM is mostly caused by bias. So one set of conclusions is overfitting is biased. The image alignment parameters, as we will see, cannot be reliably determined for 10-15%, 10 to 50% of the particles. And the same happens with the class label. And the image processing algorithm is another possible source of bias. We will not explain much about this, but this is how it is. It is explained in the longer. So here, what we have is if we have classification errors, we are again in this weighted average. So part of them give a correct volume, the other part gives an incorrect volume. So let's say that we repeat this process of classifying images. Here we did with a ribosome, and we classify into three classes. So in the first classification run, we get this distribution. In the second, we get this one. In the third one, we get this one. But interestingly, so we might think, okay, classification 1 for some reason went wrong, but then classification 2 and 3 agree with each other. But actually, we compute what are the images that were consistently classified together. So we would expect that these green images and these green images, they were the same images, but in fact they are not. So if we compute which are the subsets that have been consistently classified together, we would have this distribution. So the subsets are really, really small, meaning that images were scattered on the three classes in along the three ranks. So unless you have multiple runs and you have a tool that allows you to make this comparison that is available in Cypion, for instance, you would be unaware that the images that you have assigned to the green class in this example really the label that you have attached is rather unstable. And the same happens with an inaccurate Angular assignment. So you may do an Angular assignment with XMIP, high-res, and with rely on auto-refine. When you compare the two, and here I'm comparing the two for this protein, and then you would see that half of the images agree with the direction, but the other half they don't agree. So I don't mean that Relion is wrong or XMIP is wrong, but one of the two has to be wrong, because they cannot be right at the same time if they disagree in the angular orientation. The same happens for the shift. And this disagreement can go, depending on the protein, between 10 to 50% of the images. But what is more interestingly is that rely on auto-refine with itself. So if you run it twice, because it has some random component in the initialization, it may disagree somewhere between 12 to 38%. So the disagreement between two different algorithms is not necessarily different from the disagreement from two runs of the same uh, algorithm. And again, unless you run these things multiple times and ideally with different algorithms, you wouldn't be able, and you have a tool to make the angular comparison that again it is available in Cypion, you wouldn't be able to say which images have been correctly assigned and which have not. So, as final conclusions, the best way of getting rid of bias is to run uh, uh, the algorithms multiple times, and ideally with different algorithms to estimate the same thing, so that you can identify disagreements between the set of parameters. So let's say for an image you get this parameter, for the same image with two different algorithms you get these two, so you would tend to think that these are the true parameters and this is just an outlier of that estimation. And the best way of getting rid of variance is by averaging similar estimates. So now we would exclude this parameter and we would compute the average of these two, and the average should be more accurate than a single estimate. So let me thank our group that is the people behind all this work and making Cyber and XMIP work, and also our funders.